Good afternoon, everyone. My name is Aimee Hartono from Venus International University, and today I will be presenting a project that my partner and I have been working on these past few months, which is forecasting COVID-19 vaccine growth using machine learning. So before we begin, allow me to briefly go over the topics that I will be bringing later on. First and foremost is the introduction to subject and problem, followed by the solution that we chose, the results of our findings, and finally, what we've concluded from our research. So let's dive into the introduction to this topic. As you know, we are facing one of the biggest pandemics in the world, COVID-19. Currently, it has a cumulative total of around 332 million cases. It is highly infectious and it is spreading fast. At the current rate, attempts to stop the spread is really difficult. However, actions can be taken to minimize the risk and slow the movement of such virus. Over the years, many mutations of the virus have emerged. However, many vaccines are also being manufactured and licensed as one of the precautions one can now take. So some of the existing vaccines in the world includes as follows. I'm sure that some of them are familiar. About 9.5 billion vaccine doses have been administered worldwide. But the question is, how will this number change over the next few months, and how will it correlate with the growth of COVID cases? This is where our machine learning comes into play. So the dataset utilized in this study was provided by Hannah Ritchie and Max Rose from Our World in Data. The following dataset includes country-specific information on COVID-19 immunizations for 209 countries, consisting of 66,330 rows and 15 columns. We decided to only take the new vaccinations column for our daily vaccinations predictions analysis, while using the new cases, new deaths, and reproduction rate, all of which are smoothed over the last 7 days, as our vaccination and COVID-19 correlations analysis and forecast. Most importantly, the data that is updated on a daily basis using trustworthy public official sources. So it is quite a trustworthy source. So the models we chose for our research are Serema, or also known as Seasonal Autoregressive Integrated Moving Average, Lstm, or Long Short-Term Memory, Profit, and Var, aka Vector Autoregression. So we applied the first 3 models to predict the next 100 days of daily vaccine distributions, while we employed the Var model to not only predict the vaccine distributions, but also how it correlates with the new cases, new deaths, and reproduction rates data. With that said, we predicted that the trend of daily vaccinations would increase over time, with the Serema model showing the best accuracy, and that the number of COVID-19 cases would continue to rise, albeit at a slower rate in the near future, along with a decrease in COVID-19 deaths and reproduction rates as the number of daily vaccinations rise. Next, let's talk about how we came about our results. In the beginning phase, after preparing the dataset and pre-processing the data to obtain the required information, we identified that the data is seasonal. And so we proceeded to splitting it into training and test sets. Afterwards, we continued with the processes of the respective models. Starting off with Lstm. The first step we took was normalizing the data by scaling and translating the individual features, fitting the scalar to the data, and then transforming it. Following that, the training data is then constructed and classified into label and features sets, and the model is trained. This is using an Lstm model consisting of 50 units and an input shape containing the feature set at 1 character each. Furthermore, another 50 units and a dropout layer with a rate of 0.2 were added to the model. Next, a dense layer was added onto the model. We used Adam and mean squared error as our optimizer and loss, respectively. The model was then fitted with 150 epochs and a batch size of 8. And then afterwards, the test data was brought in using the same methods as that of the training data to be used for the prediction process. Do note that the data is required to be inversely transformed since it was normalized before, so the result can be presented in its original form. Next is the Serema Model. Firstly, the model requires the parameters to be defined during the training phase. These are known as the lag order, the degree of difference, and the size of the moving window, or P, D, and Q respectively. We confirmed that the vaccination's time series data is seasonal, once again, and a grid search was performed to obtain these parameters. So several experimentations with the parameters allowed for the models with the best AIC and BIC to be chosen, with the order and seasonal order being 905 and 00212 respectively. We then fitted these onto our training model, and the results were cross-examined and laid out onto several diagnostic graphs, which illustrate the residuals, distribution, and a couple of other evaluations of our findings. Once we were satisfied with the results, we input the test data onto the model using the aforementioned orders and plot the resulting forecast onto a graph. So this is what our diagnosis graph looks like. As you can see, the standardized residual shows a mean of 0. The estimated density on the top right follows a bell curve shape. The normal QQ values generally follows within the red line, and the correlelogram shows that its values fall within the blue range. All in all, this is quite a satisfactory result. Next, we have Profit, which is actually quite simple to utilize since it is an open source library provided by Facebook. All we had to do was fit the model on the data and forecast the vaccination data using the future dates that were generated by the model itself. Last but not least is the Var model, starting by first preparing the training set. Afterwards, each column was checked for its seasonality using the ADF, or Augmented Dickey-Fuller test, informing us to differentiate the data just once, to convert them from non-stationary to stationary. The Var model order is then decided, which is 8, and it will then be fitted to the model. Then we generated the forecast for the next 50 days, and finally inverted the data back to its form before differentiation. And then the final output was then plotted. So now we've come to the results of our findings. First, we tested the models so as to see how well it performs in comparison with the original data. And here is the performance of our Serema model. As you can see, the blue line represents the observed data, while the red represents the forecasted data. And there's quite closeness between the blue and the red line. Next up is our Lstm model performance. It has quite similar results with that of our Serema model, but there is generally a larger distance between the observed and forecasted data. And lastly, we have our Profit model, which follows the trend of the observed data, but has the least closeness to the individual values. With that being said, here are the results of our Serema, Lstm, and Profit models, in which we decided on using the root mean square error, mean absolute percentage error, and Pearson's correlation coefficient standards to evaluate their performances. Overall, the Serema model was seen to be the best performing one, being quite favorable for smaller datasets like the one that we've used, compared to Lstm, which is better suited for more complicated datasets. Using ARIMA in general is also beneficial, as the autocorrelation function can be used to determine whether there is a lack of unpredictability or whether or not data is seasonal or stationary. The Profit model, on the other hand, is shown to be the worst performing model in our experiment compared to the rest. While it requires minimal editing, making it more simple, it is primarily built to find patterns in business time series, resulting in what we assume is a less accurate model in this case. After obtaining our best performing model, we decided to use it to predict the vaccination numbers in the next 100 days. As such, our model forecasted that there will be a decrease following the previous data, continued by an upward trend moving forward. Next, we have our Var model, which we use to find the correlation between COVID new cases, new deaths, reproduction rates, and the daily vaccinations data, and predict their numbers in the upcoming 50 days. So here are the results. Although the number of COVID-19 cases continues to climb, its rate will somewhat drop as the rate of vaccine distribution increases, as we've hypothesized before. On the other hand, production rates are expected to rise consistently as COVID-19 deaths fluctuate in quantity but decrease significantly in rate, partially contradicting our hypothesis. We use the same key performance indicators to evaluate the model's performance across the aforementioned categories. It can be observed that, on average, the model works best on the new deaths data compared to the others. So to summarize, we exhibited our research on multiple methodologies in this paper, including the application of the Serema, Lstm, and Profit models to anticipate vaccination rates in the coming months. In addition, we compared the projection for the next 50 days of COVID-19 cases, fatalities, and reproduction rates with vaccination distributions to determine the association between the four categories. Finally, an evaluation process was carried out in order to assess the accuracy and benefits of each algorithm. The experiment results reveal that despite the benefits of utilizing recurrent neural networks such as LSTM, the Serema model outperforms the other two models, as proven by its lower RMSE value. Furthermore, we have yet to see a significant decline in the number of COVID-19 cases within the next couple of months. It was quite expected, to be honest. So whether or not its decreased rate is explicitly caused by the incline in vaccination distributions, unfortunately still remains inconclusive. However, in future research, the implemented models can be extended to forecast other attributes of the dataset to better understand the COVID-19 vaccination rates, for example, in different countries, and provide information as to which country would need further attention. Finally, when more data is accessible and made public in the future, it is advised that the research be repeated to assess the differences and obtain even more accurate findings for longer periods. And that is all for my presentation. I sincerely hope that you found this study as interesting as my partner and I certainly had during our research. Once again, I have been Aimee Hartono. Thank you for listening.